Decoders are also basic combinational circuit building blocks, and we call them building blocks because they appear like multiplexers, they appear everywhere as well. So let's see how they operate and what they do. So in here I'm showing you a 2 to 4 decoder. Okay, what do these numbers mean? Well, 2, that means it has 2 inputs, and 4 means 4 outputs. So what I have in here is I have 2 outputs and 4 inputs and 4 outputs. Specifically, it's actually 2 inputs and 2 to the power, well, how many inputs? 2, which is 4 outputs. That's what we have. Okay, so usually you can see n times 2 to the power n. That's what we usually have. Okay, so what do they actually do? Well, you place some sort of a pattern in here or a number on here. Let's say, for example, you decided to do this to be 0 and this to be 1, for example, which is the number 2. Okay, so you place the number 2, 0, 1 binary. So what it does, it will go to its output and will activate, or it will assert one of its output. Which one it is? It's actually the output in here. So this output will be 1, this will be 0, this will be 0, this will be 0. Okay, so let me give you another example, this time in green. So let's assume that instead what you did is you said, okay, I will do 0 and I'll do, for example, 0. I mean, that's how I can change it. So if you do 0, 0, what happens is that's what it sees as its input. It's its input. Okay, the output will go and say, well, 0, 0 is here. I'm going to put this to 1, this to 0, this to 0, this to 0. And as you can see, it's just basically you put a binary input and it just activate when it's at output, or make one of its output hot. So sometimes it's referred to as a one hot encoded output or one hot decoder. Sometimes you hear me saying binary decoder as well for this. So that's how simple it is. So what's it used for? Well, here's what's it used for, or what I've seen it used for. There are many, many, many applications that you can use it for. You can implement any logic function you can think of using decoders. However, an example that I've seen many, many times is like sometimes you have multiple logic elements in here, or blocks that they can be related or not related. It doesn't matter. What you have is you have these outputs connected to each one of them. Okay, and let's assume that you want to activate this little guy in here. So all you have to do, you connect that to its enable, for example, or something like that, and you can say, okay, which one is this? This is 0, 1. So once you put 0, 1, it gets basically the 1 gets sent out in here. It just activates this, and this will be deactivated, this will be deactivated, this will be deactivated. It's kind of like a selector. So this is one application of decoder. It's really, really useful. Other applications of decoders that you might have seen before is like, well, if you think about the implementation of the decoder, this is the truth table, which I'm going to cover in a second. But if you actually go and implement it, you'll see that it's pretty much, it's giving you the minterms of like all sorts of W0. Okay, so Y0 is just W0 not, W1 not. These are all the minterms. All you have to do is just combine them. And you can combine them by just basically, let's assume you take this input in here and this input in here, you put an OR between them, and you just implemented some sort of a function. Okay, you can implement an adder, a subtractor, whatever you want, like here. But anyway, for now, we're just going to focus on how do we build that decoder in here. Pretty specifically, how do we build that? So we're going to start by building a 2 to 4 decoder, and then we're going to expand it to bigger decoders. So let's go to Vivado and implement it. So I went ahead and I started a new file or new module here. I called it decoder underscore 2 times 4, and my ultimate goal is to implement this little guy in here. As usual, I'll start by putting what my inputs and outputs are. So I'm going to say, okay, I have an input, it's W. Well, I have W0 and W1, but just to make my life a little bit easier, I'm going to just vectorize this guy in here. And I'm going to say, well, it has to go, it's a 2-bit input, and of course the output will be output, and then we can figure out what the output is if I'm vectorizing it. Frankly speaking, I know I need 4 outputs, and traditionally I would have just written 3 to 0. However, just because I want this here, or I want to match whatever it's appearing on my truth table, as you can see, the Y in here and the Y in here, the most significant bit has an index of 0 and the least significant bit has an index of 3. They're actually different signals, so most significant and least significant doesn't mean the same thing. It's not a number. But anyway, what I'm trying to say in here is, as a designer, you have control over the indices in here. If you need 4 bits and that vector should be 4-bit, you could have just went from 1 all the way to 4. It's the same exact thing. It's just the least significant bit will have the index of 1 and Y0 will be invalid. You don't have it anymore. But anyway, to go back to this in here, what I want to do is I want to just match whatever I see in here. So I want to say, well, the most significant bit will have the index of 0 and the least significant bit will have the index of 3, and these are 4 bits. The W, I'm just going to keep it from 0 to 1 because it's the same. the convention is to have the least significant bit the smallest number and the most significant bit the largest number, but sometimes you have like diagrams like this and you just want to follow it. So that's how we do it. This is how we put the input and output. Okay. Then how do I implement this decoder? Of course, you can go and use data flow modeling or gate flow modeling or whatever it is to implement this. But at this point, I'm just focused on behavioral modeling. And I want to just show you at least 3 ways to implement this particular decoder. So let's get started. First, because I'm using behavioral modeling, I'm going to start by saying an always, and I'm going to give it a sensitivity list, and I'm going to say begin and an end. And in a sensitivity list, if I take a look at this particular diagram in here, I have the input W, and that's the only thing that should trigger a change in the output. So my sensitivity list should have just W in it. All right, so now where do I go from there? Well, multiple ways to do it, depending on what type of routing network I want. If I want to use conditional structures, which I will in a minute, I need to figure out which routing network I want. Let's assume I want it to be implemented in a bunch of small multiplexer cascaded after each other, basically a priority routing network. That means you should use an if statement. So I'm going to use an if statement. I'm going to say W could be equals 2-bit 00. Okay, and of course you have the freedom to use 0 like in decimal or something like this. I'm just, for the sake of simplicity, I'm just gonna use binary because the truth table is written in binary. Of course, at this point you can say, all right, you can either say y equals, okay, and you can specify all of the 4 bits that you want, okay, in binary 1 0 0 0. That's one way to do it. Another way to do it, which I'm going to write it in here, is whenever you say else if, for example, W equals 2-bit 01, you can just say, for example, Y, and at this point 1 equals 1 bit. Okay, but if you want to use that, you need to give Y a default value. And generally speaking, we want to give Y a default value, so just in case we forget it, and so that we don't get latches. Remember, it's like we always use default values in here for all the outputs within the W or within the always statement, so that we don't get any memory elements. Of course, it doesn't like that Y in here because it's not of type reg. We fix it, and now it likes it. Okay, just for the sake of consistency, I'm just gonna make everything is in the same format in here. Again, what I'm doing in here is I'm resetting all the Y's to zeros, and then based on whichever W is activated, I'm just making that asserted, basically making it hot. Okay, and of course we can do this here, else if, and then you can say W equals 2-bit 1 0, and now 1 Y2 this time, okay, equals 1-bit 1, and then I have else. You can use else or you can use else if. I'm just going to use else if, and then WW2-bit 1 1, okay, Y3 equals 1 binary 1, and for the sake of like completeness, I'm just going to say else, just in case. I'm just going to say Y will be, you can do it whatever you want. We can just say it's a bunch of zeros in here. Again, I do not technically need that else statement because I counted for all the sorts of the values of W, but just in case, maybe you change the size of W, you make it 3 bits, at that point that else will actually capture everything else. All right, so that's it. So if I actually just save this little guy in here and I just take a look at the schematic just to see, I expect to see a cascade of 2-to-1 multiplexers, a bunch of them, because I implemented it using the if else. So it's going to infer a priority routing network, and that's exactly what I got in here. If you take a look at it, that's what I got. Perfect. Okay, of course this isn't the only way to actually test it, so I have written a test bench. So if you actually run the simulation in here and we take a look at the output of that test bench, it should just route, or it should activate one of the outputs Y's based on the value of W. So let's take a look at this guy in here. Let's one more time. We do that, and that's exactly what happens in here. You see an 8, a 4, a 2. You might not be able to see it clearly this way. You can change the radix of one of them. Let's say I wanted the binary. That's W is 0. That means this is 1, this is 1, and this is 1, and this is 1 based on the index of the W. So that's perfect. That's exactly the intended behavior. All right, so let me now show you a different way to actually write that decoder. So if I don't want to be writing it with a priority routing network, if I wanted it, for example, with, let's say, a multiplexing network, that means I'm asking you to use a case statement, specifically a parallel case statement. Let's do that. So we'll do the case of W. Okay, we're going to do case of W, and then we're going to say end case. Okay, what do I mean by parallel case statement? Well, parallel case statement is the following. It means that you're going to match W with a bunch of numbers, and there's no two cases that are overlapping. So if W is 0, you're going to only match it with whatever you're going to put in here. If W is 1, you're going to only match it with whatever is here. If W is something, you're going to only match it in here, nothing else. That's what it means by parallel. It's basically mutually exclusive cases. There's no overlap. Sometimes you can write cases with like 0 or 1 and 1 or 2. Well, there are a couple of places, and at that point you'll be inferring a priority routing network. Anyway, so that's what I have, and for the sake of completeness, I usually include a default. Okay, so let's see. What do I want the Y to be here? I want it to be 4 binary 1 0 0 0. Okay, and then what do I want this to be here? 4 binary 0 1 0 0. The second one would be hot, or okay, binary 0 0 1 0. And of course, we do this here. That's not the last one. Okay, this one here is the last one. I do not technically need it because I have accounted for it over here with the default value, but it's a good habit to just keep. All right, so if I actually go and run the simulation, you should get the same exact answer or same exact test, but I'm just going to run the schematics in here just to see. I expect this to be replaced by a big multiplexer. I have to reload the design because it's out of date, because it's based on the previous code, which is with if statements. Okay, now we take a look at the schematic. I expect to see a really big multiplexer. Okay, and that's exactly what we got in here, a big multiplexer. All right, so is there any other way to do it? Yes, there is. Another way to do that in here is actually there's technically an easier way to do it, and here's how we can do that. All right, so an easier way to do it is I'm just gonna set the default value to that, and then you can say y of w equals 1 bit 1. So let me explain what this happens in here. So in this particular case, I'm expecting it to be, I'm setting y to be zeros. I'm zeroing out everything, and then I'm going to say y, the index w. We'll take a look at the truth table in here. So let's assume that w had the value 2. That means it's this little guy in here. And what I'm saying is y of 2, which is this little guy in here, will be 1. And that's basically I'm activating it. So it's a straightforward implementation of that. I did not use any of the routing network. It will use something else. And you can definitely go and test it with the simulation, and it should give you pretty much the same exact behavioral. No changes whatsoever. It's the same input and same output. Right, we can discard this guy in here just to make sure that my test bench is working correctly. And you can take a look at how I wrote these test benches separately. But at this point, I just want to take a look at the output just to make sure that we do this in here. That's that. And yes, it's 8, 4, 2, and 1. That's exactly what I had. And of course, you can see it in radix of binary if you choose to. Okay, so it's working. All right, so before we move on to building a larger and larger decoder, I just want to mention that most of the decoders will have an enable input. And frankly speaking, a lot of digital logic circuits will have an enable circuit. And let's take a look at this truth table in here. What does the enable do? Well, the enable is just another input that we add. Okay, and if it's 1, the circuit would function exactly as we've seen before. There's no difference whatsoever. However, if you put that enable at 0, or you deassert it, you'll see that all the output will be zeros. Nothing will be activated. So technically, if you have like all these elements here connected to it, you're going to see them all off. So how can I modify my code to actually implement that? Well, here's how. I'm going to here, I'm just going to take all my inputs and output and everything. I'm just going to copy it and put it here in the in another file, called it _enable. Okay. So up to this point, it's the same exact code. I'm just going to add the enable, and you can add it anywhere. And just to show you, we can actually add it in here. Okay, that's the enable, or you can add it in here if you want to. It's up to you. I'm just going to add it in here. All right, so we're going to do that. Okay, so we added the enable, and of course the always statement has to be changed now because I have an enable. So for the enable change, everything should change as well. I believe I need a comma in here. And the way we change that code in here is as follows. So what we need to do is we need to say, okay, let me just keep that out in here, and you can say, well, if, and you can say enable, I want that to happen, or I want basically the decoder to happen. Else, that's good habit to have. I do not want that to happen, so I'm going to say y equals 4 binary 0 0 0 0. And now I need to remove that in here, and all I have to do is just well, I'm going to keep the default value because it's a good habit. I'm just going to remove that in here, and now you can plug in whatever implementation you have. I'm going to just begin and end, and whatever implementation you like, priority routing network, multiplexing routing network, whatever we did in here, you can just implement it. For example, let's assume that I wanted to implement the multiplexing routing network in here. I'm just hitting undo, hopefully, so that I don't have to type all of that. Okay, so I will do redo in here. Okay, another redo. Okay, so I'm going to say, okay, let's implement it using the case statement. I'm just gonna do here, and here I'm just pasting this little guy in here. Okay, and here, and there you go. So hopefully it did it that way and that way and that way and that way. So if you create this, I expect to see a couple of multiplexers, one small one, which is a 2-to-1 for the enable, and one big one for the case. So let's see that schematic. Of course, you need to go in here and just make sure that this is your top file at this point. Okay, and I did also create like a test bench. I'm going to make it my top file as well. I'm going to say, okay, generate the schematic for me. Okay, and the schematic has to be reloaded, because that's the last one we actually run. And I got exactly what I expected. A multiplexer for the enable, it's based on the enable signal, and a big multiplexer based on that here. So again, if you go in here and you just create that, instead of using a case statement, you use an if-else statement. I expect that this multiplexer, the big one, will be replaced by a cascade of multiplexers, and you can test it. Let's run the simulation just to make sure that everything is functional as I expected. So the simulation now is with the enable. So it's pretty much very similar to the previous test. However, I have something in here. Let's see. Let me just do that in here. I believe it was still working, so I'm going to discard this guy. All right, the simulation ended. Let's see. So it's pretty much the same as the test before. However, I just added the enable signal in here. So the enable signal in here, you'll see that whenever it's enabled, it's actually outputting 8, 4, 2, 1, exactly what I expected. And whenever it's disabled, the output is 0. And if you prefer to see it as a binary, you can just change that in here as binary and you'll see it. So it's working. All right, so we'll move on to building a little bit bigger decoders. For example, I can take the 2 to 4 decoder that I just created. Using a couple of them, I can just make a bigger one, which is a 3x8 decoder, okay, the one here. Or I can use a bunch, maybe 1, 2, 3, 4, 5, to build a 4 to 16 decoder, actually. However, it's like what I want to do is I want to make it a little bit more generic, more parameterized basically, because if I want something a little bit bigger, like maybe not 4 to 16, but 5 to 32, I shouldn't be figuring out how to actually accumulate it in instantiation. So what I'm after at this point is to create a generic decoder, and that generic decoder will take exactly n input, will give me 2 to the power n outputs. So let's get started with that. So in here I created a file. I called it generic or decoder generic, and it contains the generic decoder code, or it will contain it. Okay, so first what we need to do is we need to make sure that it's parameterized. So I'm going to say, okay, we're going to do this here. It's parameter, okay. Okay, so it's parameterized. I'm going to call that parameter n, and I'm going to give it a default value of 3. You can give it whatever value you choose, but I gave it 3. And of course we have an input, and this input is actually w, and this time I have w actually from n minus 1 all the way to 0. Okay, I'm going to vectorize it. Of course I need to have an input that is enable, okay, just because a lot of digital circuits have it. And I have an output. It will be, I know it's vectorized, and I know the least significant, or the most significant bit will have 0. That's what we did when we did the 2 to 4. Okay, and some sort of a number in here, which we're going to figure out in a minute. Okay, and that's what the y. Okay, what is the output in here, or the significant, or the index of the least significant bit of y? Well, it depends on how many inputs I have. According to this diagram in here, I should have 2 to the power n outputs. For the sake of simplicity, we have done here, let me just open that with the enable in here. So let me just open that, and I will just open it in here. So you can see that in here I have the 0 to 1, okay? And let me just double check. The 0, like if this is 2, that will be 0 to 1, okay, if my inputs are 2. If my inputs are 2, my output should be 0 in here, and then this one here should be 3. So how do I compute that? Well, Verilog allows us to do the following. It allows us to say 2 to the power of n minus 1. And if you calculate this, 2 to the power n, which is 2 to the power 2, is 4, minus 1 is 3. That will be 0 to 3. Of course, the same goes with the 3 in here. So you have 0 to 2, which are 3 input. I expect to see 8 in the output. 2 to the power 3 is 8, minus 1 is 7, 0 to 7 is 8 bits, and that's exactly what I expected. But just one comment before I move on to writing the actual code. Whenever we have parameter, that parameter in here actually, and this particular operation, that's what I'm focused on, which is the power, is not actually implemented in hardware. A parameter is not part of the inputs and output of the module. It's just something that Vivado actually, before it runs the synthesis and the implementation, does the following. It says, okay, I have a parameter, I called it n. Whenever I see n in my code, I'm going to replace it with this particular number, 3. So it's going to reach this point in here, and it's going to 3 minus 1. Well, that's a 2. So it's going to replace the whole block here that I highlighted by 2. So that will be 0 to 2. The same goes in here. This will be 2 to the power 3, and it will calculate it to be 8. That's Vivado calculating it, not a hardware on the FPGA. And then 2 to the power 3 is 8 minus 1, that's a 7. So it will replace all of this by 7, and then it will go through the synthesis and implementation. So that's the beauty about parameter. And of course, it will change n by whatever value you pass through when you instantiate that decoder. Okay, so that's how parameters actually work. All right, so now that we have parameterized this, and we're allowed to use that if you're using parameters. If you're using inputs and outputs, this is a completely different thing, okay? It's very difficult to actually use in terms of implementation or synthesis on the board. All right, so now, because I want to describe this generically and I want to describe it behaviorally, I'm going to say I have an always, and of course, my inputs are actually W and enable, and I'm going to start by begin and end. And usually, again, I give Y, which is the output I'm interested in, some sort of a default value. I'm just going to say it's a value 0, okay, and I'm going to say default. And in here, the way we can implement it, first, I have an enable signal. So usually whenever you have a circuit with an enable signal, you'll have an if with enable, and of course else with not enable. And usually I give the output directly in here, and I'm going to set it to 0. You can set it to X if you want to. Okay, and how am I going to implement this? Well, I made Y equal 0, so I'm going to use one of these tricks or one of that code that I showed you, which is Y of W should be equal 101. Okay, so that's the easiest thing. Of course, you can do for loops, case statement, if statement, whichever you prefer. But I think for a generic case, that will be the easiest thing. Okay, so I'm going to set everything to 0 except for the one where the W is activated. I'm just going to highlight this. Okay. Of course, it doesn't like it because I didn't put this of type reg because it's part of the always. And if you actually implement that, that should give you what you expect. So let's think, what should I expect to see in here, or how would it operate? Well, I'll have to see, or I have to run a simulation. So I have created a test bench for that generic case. Okay, and let me just open it here just to see what I'm doing with the test bench in here. Let me just do that. For the test bench, I'm testing it at n equals 6. For the sake of simplicity, let's just focus with 5 at this point, okay? Or maybe 4. Let's do that 4 because it's simpler. Okay, 4 bits, that means I go from 0 to 15. Okay, so we do this here, 0, run the simulation, and hopefully we'll get exactly what we expected to see. All right, so we do that in here, and there you go. So my W is changing between 0 all the way to 15 whenever the enable is there. I don't see that W clearly, but you can definitely see it. It's a multiple of 2, so I can just see this here as a radix. For example, I changed the radix to 2. Hopefully, just one of the bits will be activated, the others will not be. You can zoom in further and just double check that, but it is working. And whenever it's disabled, you'll see that the output is actually a bunch of zeros. Can I create something bigger? And if you take a look at my code, I am passing this parameter in here, and I can create a bigger parameter or a bigger decoder, just basically a 6-input decoder. That's it. All I have to do is just do that, and you can run the simulation and it will just run that. Probably it will stop because my stopwatch will stop at 155 and won't have enough. Like the way it's written, it's not like my stopwatch is not generalized, but you get the idea. So let's take a look at this output in here, and yeah, it stopped exactly at 155 nanosecond in here, and you'll see that it's generating W. It went all the way to 29. Like if I wanted to run longer, I probably will have to play around with this little number in here.